Hi there. On this video, I will cover multi-level queuing scheduling algorithm. This requires knowledge on the basic CPU scheduling algorithm like the first come first serve, short job first preemptive, short job first non-preemptive. You've got priority preemptive, priority non-preemptive, and round robin. Now let's get started. Alright, so for the multi-level queuing, basically your ready queue is partitioned into separate queues. So you've got foreground or the interactive, you've got background or the batch processes. It may happen that process in the ready queue can be divided into different classes, where each class has its own CPU scheduling needs. For example, a common division is a foreground or interactive and a background process or batch processes. These two classes have different scheduling needs. Now, in our example here, foreground may be using a round robin, and the background processes may be using the first come first serve. Scheduling must be done between the queues. So for this kind of situation, multi-level queuing scheduling is used. Now let's see how it works. Ready queue is divided into separate queues for each class of processes. For example, let us take three different types of classes or processes. So you've got the system processes, you've got the interactive processes, and you've got the batch processes. Right? So the level of priority is from high to low priority. So system processes is given the highest priority here, and for instance that is on Q1. Interactive process is given the next higher priority, and it's in Q2. And batch processes is said to be in the lower priority, and it is on Q3. So all three processes have their own queue. Now considering this figure, right? So all three different types of processes have their own queue. So each queue have its own scheduling algorithm. For example, Q1 here uses round robin, and Q2 maybe uses also round robin, while Q3 uses the first come first serve CPU scheduling algorithm. Alright. Now, scheduling among the queues, what will happen if all the queues have some processes? Which process should get the CPU? So to determine the scheduling among these queues, it is necessary. So there are two ways to do so. First, you've got the fixed priority preemptive scheduling algorithm. So each queue has an absolute priority over the lower priority queue. And on fixed priority scheduling, an example of this is serving all the processes from the foreground, then from the background. So any background process cannot start unless there is a foreground process on the queue. And if the background processes are currently being executed, and there is a new process that is classified to be a foreground, that background processes will be preempted to give priority for the foreground process. So foreground process will be given the highest priority on this fixed priority preemptive scheduling method, whereas the background process will be given the lowest priority. Alright, so there is a possibility for starvation with this fixed preemptive scheduling method. Let us consider following priority order. So for instance, you'll have Q1, Q2, and Q3. According to this algorithm, no process in the batch queue or Q3 can run unless Q1 and Q2 are empty. So if any batch processes on Q3 is running and any system Q1 or interactive process Q2 enter the ready queue, the batch process is preempted. So same thing. So if we are using two queues or 3 queues, so there is a priority being followed on multi-level queuing. Okay, and on fixed priority preemptive scheduling method, our example that is to be presented later on uses only the 2 queues. All right. So next is time slice, or the time slicing. So in this method, each queue gets certain portion of the CPU time and can use it to schedule its own processes. For instance, Q1 takes 50% of the CPU time, Q2 takes 30%, and Q3 takes 20% of the CPU time. Each queue gets a certain amount of CPU time, which it can schedule amongst each process. For example, if you are using a 2 queues, 80% for the foreground and 20% for the background process. Alright? Now my example here follows the fixed priority preemptive scheduling algorithm. Right? So we have divided the processes into 2. You've got the foreground and the background process. So for fixed priority preemptive scheduling algorithm, we have to give highest priority to the foreground process. That's why in here it's indicated by 1. Right? On the table, 1 means foreground process, and it is the first priority. Now the foreground process here is asked to use round robin with a quantum of 2. Alright? And the background processes are denoted by 2 on the table, and this you'd use first come, first serve. Alright? Now considering this table here, we have 4 processes, P1, P2, P3, and P4. Right? So the arrival time is at 0, 2, 4, and 5 respectively. Burst time 7, 4, 1, 4 for processes P1, P2, P3, and P4. Right? So amongst these 4 processes, process 1 and process 3 are considered to be background process, and this should use the first come first serve basis. Right? Now process 2 and process 4 are said to be a foreground process. So based on the fixed priority preemptive scheduling, right? So the first priority should be executed first before giving the instance of execution to the background process. Right? So that means at time 0, right? At time 0, process 1 is the only process on the ready queue. No other processes are in there. But it happens to be that process 1 here is a second priority, or the background process. So the CPU has no choice but to execute the background process P1, since there is no foreground process yet on the ready queue. Alright, so P1 will be executed, right, until when? Until 2 milliseconds. Right? So because at 2 milliseconds, process 2 came in, and process 2 is said to be the first priority, or the foreground process. So what will happen to process 1 is that it will be preempted to accommodate the first priority process, process 2. Right? So in this case, process 1 will be terminated after 2 milliseconds, and therefore the burst time of 7, we're able to execute 2 milliseconds, so we'll have remaining 5. Alright? So after 2 milliseconds, process 2 will be executed. So take note that this is the first priority. Alright? So, and since this is the first priority, so the requirement says that we have to use a round robin with a quantum of 2. So process 2 will be given 2 milliseconds to execute, and that will end up at 4 milliseconds. Alright? So at 4 milliseconds, process 3 is already on the ready queue. Right? So at 4 milliseconds, we have 3 processes on the queue, namely P1 with 5, P2 with remaining 2, and P3 that requires 1. Right? But amongst these 3 processes, P2 is said to be the foreground process. Right? So it will continue the execution for P2 for another 2 milliseconds. Alright, so P2 there, quantum of 2, that will end up at 6 milliseconds. Right? Take note that during the execution of P2, process 4 came in. And process 4 is considered also as the highest priority or a foreground process. Right? So immediately after the execution of P2, right, P2 will be terminated now, right, because it has finished the execution, it has completed its execution, which requires 4 milliseconds. Right? So right after P2 execution, so P1, P2 is done. So you've got P1, P3, and P4 is in the queue. Now amongst these three processes, P4 is the highest priority. Alright? So P4 is also a foreground process and therefore will be given another 2 milliseconds. Alright? So in this case, P4 will be executed for 2 milliseconds. That would yield to 8. So after 8 milliseconds, still we have 3 processes on the queue. So namely P1 with 5, P3 with 1, and P4 with 2. Right? It was able to execute here 2 milliseconds. The burst time there is 4, so that means it has a remaining 2 milliseconds here. Alright? So after 8 milliseconds, still there is a first priority process on the ready queue, and that is still P4. So the execution will continue with P4 until 10 milliseconds, and after 10 milliseconds it has served already its burst time. So that means after 10 milliseconds, process 4 also has completed its execution. So at 10 milliseconds, process 2, which is said to be the first priority, and process 4 is also a first priority or foreground process. So we were able to execute the foreground processes after 10 milliseconds. Alright? So after 10 milliseconds, we have 2 more processes on the queue. Right? And that was process 1 and process 3, which is the second priority or the background process here. Okay, so the background process based on the given should use the first come first serve. Alright, so next P1 will be executed because it came in first. Right, so from here after 2 milliseconds, we all know that P1 was preempted and has a remaining of 5 milliseconds here. So therefore, that 5 milliseconds will be executed, okay, resulting to 15, and then after 15 milliseconds, your process 3 with burst time of 1 will be executed. So this will end up at 16 milliseconds. Alright? Now, P1 here was executed, okay, so using first come first serve, but take note, this is a preemptive algorithm. Why? Because the higher priority came in, so therefore process 1 has been preempted. Alright, process 2 and process 4 were foreground processes, right, and it was executed with a quantum of 2. Now after all processes under the foreground process was executed and completed its execution, so it will resume with the background processes using first come first serve. Alright, so now that we get the Gantt chart, so the next thing to do is to get the table. Right, so let's get the turnaround time here. So turnaround time for process 1. Process 1 has completed at 15. Alright, so that would be 15 minus the arrival time of process 1, which is 0. So that is 15. Alright, next, process 2, turnaround time. Process 2 has completed the execution at 6 milliseconds here, but it arrived 2 milliseconds late, so therefore that 6 minus 2 results to 4. Alright, process 3, right, completed at 16 milliseconds, minus the arrival time of 4, you've got 12 milliseconds. Alright, so for process 4 here finished at 10, but it arrived late at 5, so therefore process 4 turnaround time is 5, right? That's 10 minus 5, you get 5. So total is 36, and 36 divided by 4 processes would be 9 milliseconds for the average. Alright, now let's take the waiting time. Okay, so starting with P1 waiting time, initially it never waited here at 0, but it was preempted at 2, and therefore resumes its operation at 10. So 10 minus 2 here is the waiting time for P1, so that would be 8, right? Minus 0, so that would be 8. Now for process 2, so process 2 waiting time here is at 2 milliseconds, right? So 2 milliseconds minus the arrival time of 2, that would result to 0. Right? So process 3 from the Gantt chart waited at 15 milliseconds, but it came late at 4, so that's 15 minus 4, that would be 11 for process 3. For process 4, okay, so again from the Gantt chart, so process 4 waited here at 6 milliseconds. So 6 milliseconds minus 5 there, so that would result to 1 millisecond. Alright, so the total waiting time is 8 plus 0 plus 11 plus 1 would be 20. Alright, so 20 divided by 4, getting the average, so you've got 5 milliseconds. Alright, so that's it for the multi-level queuing. Alright, so thank you for watching.